Okay, hello everyone. I'm Nikos. I'm part of Expedia Group, and I currently live in London. But I'm very glad to be back in Athens for the first time at Voxxed. I once spoke at Voxxed Thessaloniki, so first time in Athens. I hope you will enjoy the talk today, which is about the work our teams have been doing in a very niche space, which is the intersection between software engineering and reliability slash platform engineering. While working in this deck and revisiting this deck yesterday, I did some reflection. Sometimes it's good to do that in life, isn't it? And I thought about how it all started, which was back in Thessaloniki, where I studied in electrical and computer engineering. Then I moved to Edinburgh for a year to do a master's in computer science there, and focused on high-performance computing, software engineering, and also spent some time researching a space called machine learning on source code, which unfortunately back in time was not popular at all, but now you see GitHub Copilot and OpenAI and all these companies doing amazing things. At that point of time, it was the time when the Scottish people decided to have a referendum for their independence, and they thought it's not a good idea to stay in Scotland. So I moved down to London, which is when Brexit happened and the referendum. I thought, okay, maybe it's not the best idea to move to a third country and cause another referendum. So I stayed in London, where I started I joined Hotels.com, one of the iconic brands in the travel sector, with millions of customers and pretty decent scale. So I moved to London. I worked there in web engineering, building features for the websites. I worked in multiple domains, one being the authentication identification domain, the reviews domain, and a few more, but also in developer productivity, where we had a few issues that we wanted to solve, and we introduced what we call the paved road experience for our engineers. And then I continued at Expedia Group, still the same umbrella of companies, but much, much bigger scale. And my focus right now is on distributed systems, where I'm leading teams working in platform and reliability tooling. It's a pretty exciting area, especially when you do that at that scale. We will see the scale in one of the next slides. I'm also leading Expedia's open source group. If you're interested in open source in general, you can go to github.com/Expedia group, and you will find a lot of our projects being open sourced. The agenda for today, we will do a brief introduction to reliability engineering, the importance of on-road platforms and an on-road experience, especially in big companies. And we will also present the work we have been doing in two very ambitious projects. One is chaos engineering and the platform we have built internally, but also the automated region failover, where we automatically shift traffic between different regions in our cloud provider, which is AWS. And finally, key takeaways. This is Expedia's scale. We started the transformation 2 years ago, and we came with all brands together. This includes very, very popular brands like Expedia, Vrbo, HomeAway, Trivago, Hotels.com, and probably more than 20 more brands in the travel sector. And we came together, worked together, and tried to consolidate and build a single platform, single tooling, one, let's say, entity. And the scale right now is more than 35 functional domains. You can think of cars, search, flights, orders, etc. We have more than 15,000 applications and microservices. And the majority of them will be moving to the common runtime compute platform, which is based on top of Kubernetes. And we expect to have more than 500 Kubernetes clusters running across a fleet of tens of thousands of nodes. As you can see, the scale is pretty big and scary sometimes if things go wrong. And because we want to be as resilient and as available as possible for our customers, we run in a multi-region way. As a company, we are in AWS, as we said earlier. We rely on a lot of AWS services and deploy the majority of our services to more than 3 or 4 regions. At that scale, you need to focus a lot on resiliency. And across the industry, when we look at big companies, we can see a couple of strategies when it comes to reliability engineering. We see one strategy which is more proactive, more reactive, excuse me, the first one, and the one you find in most companies. When you start, you are there to keep the company running. You don't invest much in reliability engineering. And the model in these companies is that we have SREs, either a single team taking care of all the services and their resilience, or multiple SRE teams per domain. And this applies to us too. We have, as we said, a domain for cars, a domain for flights, and we have SRE teams embedded in these domains. But then the problem you realize is that these teams are working in silos and there is no cooperation. And for us, what has worked or what we are trying to do right now is to have teams working in platform health tooling, that is building tools for observability, incident management, canaries and progressive deployments, concepts like that, or even chaos engineering, as we will see in a bit. And so we have teams building tools that can be used by the domain SRE teams and the application owners, but also this center of excellence, which acts as the bridge between the domain SREs and the teams that are building these tools. To get the most value out of investment when you build tools at that size, it helps a lot if you have a non-road platform experience. Expedia was in a situation where our engineers had a ton of flexibility in working in different languages, different platforms. And we ended up with multiple runtime platforms, multiple observability tools, even multiple service meshes across different brands. And then we started this consolidation. And our target goal was to build a common set of tools. This includes a single runtime compute platform where containers will be running on top of Kubernetes, as we said. A single observability tool, a single service mesh, and all these should integrate together. By doing that, you get a lot of benefits because you can then invest in these tools. You can invest in documentation, and you can even hire specialists in these technologies. In machine learning, we have this concept, which is called gradient descent. What we try to do with gradient descent is that we try to optimize an objective function. This concept applies to this paved road experience in the sense that it is not simple to do, and if you don't do that, you end up with local maximum. But if you achieve to do that, you will end up with global maximum at a much bigger scale. Okay, so now we will talk a bit about 2 of our key projects. One is the chaos engineering project that I'm mostly focusing on with my teams. How this started, again, we had many tools in that space, more than 20 tools. And we stepped back and we said, okay, this is not going to scale. We won't be able to support all that for the entire company. So we worked on consolidation first, and then on a single vision on how can we create a single platform for chaos engineering. And this platform should integrate with our common tools. Let it be the observability platform, the service mesh, the runtime compute platform. For those who are not familiar with chaos engineering, it is a bit of an advanced concept that goes back to Netflix. Netflix was the first company to promote or even introduce, I would say, this discipline. Chaos engineering is a discipline of experimenting to ensure that the impact of failure is mitigated. And it follows this cycle, which may remind you of the test-driven development, although it is not testing. You first define your steady state. That is, my service X is healthy, based on some metrics. Then you create a hypothesis. For instance, when terminating one of the instances of this service, then I expect my service to keep being healthy. As a third step, you inject a failure, which, as we will see, can happen at many different layers. Let's say terminating one instance of my service. And finally, we observe what happens. It's more of an experimentation, ideally scientific too, but we know that it's not very easy to do that in the industry. And the verification part here could indicate that our alerts are not working and we should fix them, or that there's not enough capacity and we need to introduce or tweak our auto-scaling. And this is what we have right now after working on that for quite a few months. We have a platform internally that our engineers can use. They can go to Spinnaker, our chosen continuous delivery platform. They can use a nice UI, and they can execute chaos experiments in the infrastructure. Behind the scenes, the brain behind all that is an agent or a custom Kubernetes controller, if you're familiar with that receives instructions and then injects these types of failures into the workloads. This project is an open source project by Datadog, and we work a lot with them in the open. And as you see in this image, we have a contract between that agent and the users. The contract says container failure, which means that it will terminate containers. Then the controller is receiving this contract, is receiving this event, and then spins up these injector pods that will inject the failure to the infrastructure. And these injector pods have all the permissions, because handling permissions is pretty hard in this architecture. What are the fault injection types supported by this platform? Again, all this comes from the controller. On our side, what we have done, because there are just too many failure types that one can think of when we are talking about distributed systems. And we have categorized them into state ones, resource, network, and request ones. On the state side, we can terminate containers, pods, whatever. We can terminate nodes. Then on the resource side, we are talking about stressing the CPU, stressing disk, things like that. Network is the widest category. You can drop packets, delay them, TCP packets, or even corrupt them, and even do some very wide failures, like disrupting the network in a particular availability zone. So it has a pretty massive impact in a cluster. The architecture right now, although I wouldn't focus too much on that, I know it's a bit complicated, but let's focus on a few parts. The first one is, again, the whole developer experience of that, because that's too low level for our engineers. And the engineers will be going into a UI, as we will see in the next slide, click buttons, select their cluster, and then execute an experiment. On our side, as a team, we have built a Spinnaker plugin. Spinnaker has this nice pluggable architecture, and you can create custom plugins. This helps you customize the UI. It helps you customize the server-side components it contains. And then you can see this control plane too, which is our abstraction on top of Kubernetes. The whole reason behind this control plane is that because we have hundreds of clusters, we need to be very careful with security, with auditing, compliance, and how these changes are propagated to what we call worker clusters. At the end, the worker clusters are the clusters where all the workloads are running, or the applications are running. And this is what the engineers care about. This is the UI, which is hopefully more intuitive than the previous architecture. You can see that the engineers can go to Spinnaker, where they do their deploys for their applications. They can add a custom state, selecting the cluster coordinates, let's call them like that, which has to do with the whole control plane and the abstraction. They also provide their experiment, and then they can see the flow of that experiment in the UI. Has this been injected? Has it failed? And so on. We also provide a few useful links to them that can help them verify the whole impact. For instance, links to key signals, like rates, error rates, latencies, and so on. One very interesting challenge when building these platforms is how do we test them and how do we debug them? And for this, we make use of a set of demo resources that are provided in this repository, the chaos controller, where we have, let's say, one application, one curl application calling an Nginx web server. And like that, we can see the impact of injecting failures in the network. In addition to that, we have built a very simple web application on our side with REST endpoints, gRPC services, and again, we can call these endpoints to understand the impact. This is good so far, but what about the operational aspect? Let's say you build this platform. How do you know this is working across hundreds of clusters? And for that, we have created dashboards that give us the view. Are these containers and agents running? Is there an issue? We have alerts too. There is also the question of what is the business value of all that? That sounds complex so far, but what is the business value? And we need to work with our leadership. We need to work with the product side too for that. What helps here is to have a data-driven approach. In these tools, one of the key metrics is adoption. How many engineers are using this platform, right? And for that, we have this dashboard that can easily give us this kind of numbers. We can say that at this point in time, we had 50 or 100 experiments running. It also helps us understand if there is an impact to track down the root cause, because it can tell you if an experiment is running in a particular cluster right now. After building this platform, and even more when we start these very ambitious projects, it's very critical to think about success and exit strategies. And one of the key aspects in that is how do we promote these tools across thousands of engineers? Because Expedia has many thousands of engineers. For that, we use a couple of tactics. One is we have created a set of bite-sized videos that we promote in newsletters and blog posts. We also write internal success stories whenever we partner with our engineers. Then we have public blog posts too, hopefully also interesting for the wider audience, not just for our engineers. And finally, this is something we thought about recently, is we have more than 35 domains. How can we scale that? We are a small team when compared to the whole company. And what we do is that we organize sessions with the architects of our domains. They provide their architecture, the architecture of the entire domain, not just one or two services. And then on our side, we identify the failure points in these architectures, what could go wrong there, and opportunities to use chaos engineering for that. And as you can see, this brings down the number of engineers we need to target from thousands to just 35, because we can work with them more easily. And then we focus on a particular part of these architectures and experiment just in that part. This reliability hub is something that we introduced recently. The problem we had was that in the platform side, we build a lot of tools, but how do we promote them and how do we provide a single view of what our teams are doing? Otherwise, the way our engineers will see us is you build tool 1, 2, 3, 4, whatever, but how do I know how I can use these tools? Is there a single page or a hub? And we created this hub which aims to provide first guidelines for engineers that want to improve the resilience of their systems. And these guidelines are very similar to what Microsoft Azure or Google Cloud published. But we try to make them practical, which is the whole point of this hub. And it also aims to raise awareness of the reliability engineering products that exist inside the company. Because at that size, sometimes it's very critical to provide visibility of products and tools. And how do we make them practical rather than just another set of guidelines, which is very common with documentation? We have a section called best practices. And by best practices, we mean circuit breaking, timeouts, bulkhead, etc. And then for each of those, we have 2 entry points on which we can rely. One is the common platform, because some of them are implemented in the common platform. And the second entry point is language tooling, the SDKs that we use in the company for Java and so on, and the templates that these teams have created to bootstrap new applications. And like that, we have 2 good entry points that we can leverage. And finally, we have a section called how can you verify that you have implemented this in a right way? And this is where case engineering comes into play, because you can verify your circuit breakers and the configurations. You can verify your timeouts. Okay, that was chaos engineering. Now to the next one, which is a bit more ambitious, I would say. That one is the automated region failover product we have been working on. If you see in this picture, there are a couple of regions. If you're familiar with regions, these are distinct geographic locations where cloud providers are having data centers. We are in AWS, and let's say we deploy our services to the blue region and the green region. How many of you are familiar with fault domains and failure domains? Okay. Could someone give a brief description of what a fault domain is? Or what do we mean by that? Anyone? No? I think there was someone from that side. Okay. I'm going to do this then. It is, again, the phrase of what happens in Vegas stays in Vegas. And what this means is that we don't want to have cross-region calls starting from one region in the request flow and going to another region. And this is for multiple reasons. It is, again, security compliance, but it is also the increased latencies we see, which are very critical for specific domains like the search domain. Now imagine a request comes into our website, and there is a load balancer that is routing this request to the closest region based on a geolocation. We use the load balancer term in a very generic way. It could be a content delivery network, could be one type of, a different type of a load balancer. But what matters is that the request that comes to a particular region stays in that region. And now let's assume that there is an incident in that region. If you have followed in general the news over the last 2-3 years from cloud providers, there have been many big incidents where entire regions went down and services in those regions went down. So what if there is a wider incident in a particular region? In that case, the first option is to move all the traffic to another healthy fault domain or region. But this has a couple of problems. The first one is that we also move healthy traffic. It can't be the case that the entire region is down, isn't it? The second problem is that it is difficult at that times and at that scale to find and provision that traffic, because Netflix and other companies will need to have capacity in the other regions because region green is down. But what if the failures are small and isolated, like the one you see in this picture? What if only one cluster, or even better, a single service, or 10, 20 services in a single cluster are down? In that case, we can have a gradual region failover, which of course is much more difficult to implement. How can this be implemented? We thought of two ways for doing that, depending on the level and granularity we need. The first one is doing this at the DNS level. But, sorry, I have this slide first. Okay, so you can see the boxes here and the regions. We have 4 regions. You can see the blue boxes, which are clusters. And there is also a pilot that is receiving instructions and then redirecting traffic based on DNS. And so the first option we have here is to do that through DNS, and we mentioned the problem with that. So the problem with that is that DNS records are cast everywhere. So it takes a lot of time to propagate these changes. We need to wait for quite a lot of time. The second option, I'm not sure how many of you are familiar with service meshes, which is just another infrastructure layer that abstracts cross-cutting concerns like security, authentication. And in our company, we have adopted Istio as the service mesh. And we can benefit from traffic shifting features of a service mesh, which are already there. In that case, if we step back into the previous diagram, what we see here is that there is a failure in the top right, or an incident in the top right region in one of the clusters. And there is one cluster in the bottom right image that wants to send traffic and do calls in the affected region. In that case, what we can do is redirect this traffic all the way to a healthy region and cluster. Again, this it might sound simple, but of course there are many complexities when implementing that at that scale. And a few of the very critical capabilities when implementing that are the ones you see in this image. First one is that we need to ensure that we have provisioned the infrastructure that is needed. We might need to scale up and provision more nodes, for instance. We also need to ensure that we have scaled up all the workloads, all the applications, and that they can receive all this traffic that is evacuated. We're also working on what we call custom actions, where engineers will be able to run a job before this happens. For example, they might want to replicate databases, things like that. And finally, when we presented this platform to our operations teams that are on call, they really wanted to have a gradual traffic shift, because we don't really want to shift 100% of all that traffic to other regions. It's going to be a pretty massive task that can always fail. And what we do is we give the option to shift based on percentages. You can shift 25% of that traffic now, then 30, then 40, and so on. It's very similar to the canaries concept and progressive deployments, and how our engineers are deploying their applications. Okay, so what are the key takeaways and what have we learned over the last 2 years when working in such tools? The first one is if you can invest in proactive reliability rather than in reactive only. And use tools to facilitate the prevention, but most importantly, the recovery, because you will find out that you can automate a lot when it comes to the recovery mechanisms. Then again, you can use chaos engineering, as we said, to introduce failures and even practice incidents, because after all, we know that incidents will happen. It's a matter of when, not a matter of if. And as long as you practice incidents with game days and exercises, you will be able to better recover from these incidents. Second one, and we have seen that whenever companies and brands come together, consolidate tooling as quick as possible, because otherwise you will end up with too many languages, too many platforms, too many tools. And this will reduce fragmentation. It will avoid the whole cognitive load on the platform side, but on engineers too. It will also allow you to invest in tooling and in integrations, in documentation of these tools. And finally, and I would say the most critical, focus on the customer. You should first identify your customer, which most of the times will be the engineers of the company. As long as you know your customers and you have a strategy on how to approach them, then you can work with them, you can get feedback, you can also work with your product side. And the most critical, provide great developer experience, because if you don't do that and you just present the low-level details of these frameworks, they will not use these frameworks. You need to have great developer experience with nice UIs and so on. And if it is possible, I know that this mostly applies to much bigger companies, invest in developer advocacy. You see a lot of roles in developer advocates or evangelists right now. And the reason is that there are just too many things happening in tech. You can't do all of them. You can't target or learn all of them. So you really need people that understand 1, 2, or 3 tools, and they can then promote these tools. And with that, I'm closing the presentation. Thank you very much. Do we have any questions? Yes, sorry.
Usually, when there's a region-wide failure, it's most usually about the primitive part of it, network storage, the hard part, cannot control at all. So my question is, why are you trying to solve a regional-based issue using more high-level tooling, such as a mess like Istio, for example, instead of using, again, the same low-level primitive structures, such as the DNS mesh? Did you try and fail, or haven't you tried to fail? Because you know that DNS is very good with caching and things like that happening around the globe.
Thanks for the question. We had this opportunity to use the service mesh. That's one thing, because this was rolled out across the company. We also tried with DNS at the beginning, and it just didn't go very well. We needed better granularity. But to that question, I think it's important to mention that what I have seen in the platform, even with chaos engineering, you can do that at many different levels. At the end of the day, it's about which one you choose, which might not be the best, but if it works for you, that's fine. And we had the same argument with chaos engineering, because initially we wanted to follow a similar design and leverage the mesh for that. But then we thought, now we have Istio, but what if 5 years down the line we don't have Istio and we have a new service mesh? These technologies come and go. And for chaos engineering, we chose exactly the opposite approach, which is at the lowest level possible of the Linux kernel. And this is what this chaos controller is doing. And with that, we know that at least Linux, it's not going to change for a couple of years. So that was our decision. Yes? I'm afraid I cannot answer the question from an implementation point of view because I personally haven't worked on that feature. And it is something we're still working on. I know we have achieved the whole percentages, but I really don't know the low-level implementation details. Yeah, sorry. Any other questions? If you're interested, I didn't add the slide, but we are hiring across the globe. Expedia is a pretty big company. We have thousands of roles open. And we have an office in Athens, too. But I'm not sure if we have many engineers here. Thank you.